Software Engineering Radio, episode 89, Joe Armstrong on Erlang. This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast. Hi everybody, welcome to Software Engineering Radio. So here is some information about the SE Radio get-together. As you know, this is our Open Space Conference. It's in autumn of 2008. It will happen on October 16th and 17th in a thing called Kloster Hornbach near Zweibrücken, Germany. It's actually directly next to Zweibrücken Airport, which doesn't mean much. It's a very small airport, but anyway, we would like you to come. We would like to have a lot of interesting discussions there. You'll have to submit a position paper to team@suradio.net so we can see you actually have interesting ideas to talk about. We want this to be really a lively discussion. We also have a nice dinner sponsored by EX. They agreed to sponsor the conference and make sure we have a nice dinner on Saturday. So why don't you visit the website and look at the details and then join us at the SE Radio Get Together conference. You can do us a great favor by mentioning SE Radio on your own blogs and other and websites. Helping us to make SE Radio more widely known is very useful to us, and be sure we'll thank you for doing it. Okay, I guess so that's enough for the meta stuff. Let's go ahead with the content. This time we are talking to Joe Armstrong. I'm always tempted to say Joe Erlang because he's the Mr. Erlang, I guess. So welcome, Joe.
Thank you.
Before we actually delve into the topic, I'd just like to say thank you to Trifork, the organizers of Joe, because they gave us this room inside the Trifork offices, so we have a quiet spot to do the interview, which is always useful. So, Joe, why don't you give us a little brief overview of what Erlang actually is, how it was created, and why anybody cares today? What's the big deal?
Well, what is Erlang? The answer in a nutshell, I suppose, today would be it's parallel programming without the pain. Parallel programming is perceived as being something which is rather difficult, and I think this is due to not the problem of parallel programming in itself, but the way that people perform parallel programming. There are basically two models of parallel programming. One involves the idea of shared memory, which is protected by mutexes and locks, and that method of programming is extremely difficult. Erlang takes a completely different approach and uses what's called a pure message passing paradigm. So there's no shared data, and in Erlang, everything is represented by a process. Processes communicate by message passing, which makes concurrent programming a lot easier. So the message is that Erlang is a language which makes concurrent programming painless.
Okay, and processes are obviously not the same as operating system processes. It's very lightweight.
No, they're very lightweight objects. They in Erlang, processes belong to the programming language, and not to part of the operating system.
There is this general idea of actors. I guess that's close.
Yeah.
Okay. So when was Erlang created? What was the context in which it was in? What kind of systems was it built for?
It's difficult to put a first date to it because there was never a project to make a new programming language, but the work that it derives from started in 1986, and it was done in the computer science lab at Ericsson. Mm-hmm. At the time, we had the problem of just really trying to find a better way of programming telephony and of programming big switches. This was Ericsson's core business.
Yep.
And we just started tinkering around with different programming languages to see how we could program telephony. Now, telephony is a problem where you have hundreds of thousands of people all connected to the same switch, all doing independent things. And so the problem is very naturally concurrent. And inside Ericsson, there was a strong tradition of building concurrent systems, which are also fault-tolerant. The other aspect of the problem is that unlike desktop systems and commercial systems, telephony systems have to be upgraded without taking them out of service. So I think when we started work, we were looking at a way of handling massive concurrency, hundreds of thousands of people being controlled by one switch. We also wanted these systems to basically run forever, because if we needed to change the code, we have to do this without stopping the system. So in about 1986, we started looking at how to do this. And I think the first version of what you could call Erlang was in 1987. And this I wrote in Prolog.
What?
Well, I started with Prolog, which, I really like Prolog. And
Write one new weird language in an old, even weirder language.
Prolog's not a weird language. Prolog's a very beautiful language. I can't really understand why everybody doesn't use it. But Prolog isn't very good at certain things. It's not very good at doing concurrency. So all I did was add concurrency to Prolog, and so you could have lots of Prolog processes all running at the same time. Of course, this was extraordinarily inefficient. But the programming model was very attractive. So that's how it started.
The focus is on concurrency. So the reason why it's becoming, popular, hyped, relevant these days is obviously the multi-core stuff, right?
Yeah. I think really, Erlang's a language which is 20 years old, and for about 18 of those years it was just being used internally inside Ericsson. So nobody's really interested in it. A few sort of devotees on the outside world used it. But it didn't have any widespread popularity. I think when you have concurrency or threads or anything like that which run on a sequential processor, you don't actually have concurrency. You have multi-scheduling. Yeah. The operating system schedules between different processes, and that's not real concurrency. So there's no benefit. Actually, your programs will go slower if they're multi-threaded because they've got the extra overhead of scheduling. But when you have a true multiprocessor, things actually start going faster. Yeah. And that's a radical change.
So in your presentation, you call this a real significant paradigm change that needs to have changed a better approach to actually.
Yes, absolutely. I think the other thing that happened was from about 1986 or 1985 to 2002, sequential processors got faster on average by about, 65% per year.
Something like that. A lot.
Yeah. And from 2002 to 2004, that slowed down to 20% per year. And the reason for that was that chips got bigger and bigger and bigger, and the clock frequencies got greater and greater and greater. And so in about 2002, we got to a situation where in one clock cycle, you couldn't reach all of the chip.
and that was a pretty fundamental issue.
Well, yes, it was predicted by some hardware guys in 2000. Yeah. And they wrote a paper saying the end of the road for instruction level parallelism. What that means is that chips as from about 2002 actually go slower, because the solution to that problem is to not have one whacking great big chip which gets bigger. It's to break it into small cores on the same chip. Yep. So actually programmers have had a free lunch from, all throughout the mid-80s and 90s. They could add more and more bloated features to their code. Their code could go slower and slower and slower, and they were saved at the end of the day by a faster clock speed. Yeah. I mean, you must remember the
Amstrad CPC.
What was it, 40 megahertz back in 1985? And now we have 2 gigahertz.
Yeah, sure, yeah.
So programmers actually didn't have to do anything. Now, I don't know if they were aware of that fact. You see, and I think when their boss sort of congratulated them and said, wow, your new program's got a lot more features in it. See, it's not slower. You're an amazingly smart programmer. I think a lot of programmers actually believed that it was due to their super smart code. They'd ignored the fact that the processor had got faster. Yeah. So that trend stops in 2003. What happens then is that the sequential processors start going slower. Yeah. So if you want, if
pretty different.
Yeah. And I think there's going to be, let's see what will happen. I think after a year or 2 years, there'll be this gap which people will start to notice. And then after 3 or 4 years. And then a funny thing's going to happen. In 2009, Intel, according to their roadmap, will bring out the KFIR processor, which has got 32 cores. Yeah. And some poor programmer is going to be sitting there and they're going to have performance problems with their program. And the boss is going to look at the CPU measurement on the machine and see that let's say it's using one of these 32 cores at 100%. And he's going to say, wait a moment, you're telling me you've got performance problems and yet we're using 3% of the CPU? Come on. Yeah, sure. The trouble is, in order to use that other 97% of the CPU, you have to write a true multi-threaded application.
Yep.
Now, Java programmers know all about thread-safe applications, and they also know that when you go from a sequential processor to a parallel processor, the program probably won't work. Well, actually, I don't think they do know this.
Yeah, but they will.
But computer scientists know this because the programs interleave in a different way, and a whole new load of bugs are going to come out.
Yeah. Okay, so in the book you recently wrote, which is called Programming Erlang, a pragmatic programmer thing, we put it into show notes. You started actually by motivating a new approach to programming, which you called Concurrency Oriented Programming. And you didn't say it's object oriented with concurrency or functional with concurrency. You kind of tried to coin, or you did coin this new, moniker for a completely different approach. So can you characterize what this concurrency-oriented programming approach means as a whole? What are the ingredients to making it?
Yes, it's a style of programming where you use concurrency to structure the application. I mean, that's the simple answer. And it's a style of programming which maps onto the real world, because we live in a concurrent world. So anybody who tells you that we don't is an idiot. Wherever you look, you see things happening in parallel. People are walking around a room, cars are buzzing along on a motorway, something like that. Yep. Now, to model that in a sequential language is a complete nightmare. It just doesn't make any sense. Yep. So as I see the world, I see objects which communicate. I mean, we're sitting in a room having an interview, and if I were to model that, there's Marcus, he's one process, Joe's another process. I'm sending messages to him. He's just sent me a message. A visual message. The message was, move the microphone nearer to your mouth because the microphone was drifting off. That's a message. Yep. And we don't have shared memory. If we had shared memory, Marcus and I would be a Siamese twin and we would communicate, through some neural passage. But we don't work like that. The world doesn't work like that. And modeling it like that, I think, is a disaster. This is shared memory programming, which is a deep sort of, there are two models of concurrency. There's shared memory processing and this message passing processing. So the concurrency oriented programming bit, that's the model of what we're doing. You see, you have programming languages and then you have modeling languages. So if you take the world of objects, the programming languages are object oriented languages. They're languages like Java, C++. And the way you model the world, the way you think about the world, is in terms of objects. So if you go to the Erlang world, the programming language is based on pure processes and message passing, but the way we model it is a concurrency model, and we map the concurrency model from what we observe in the real world.
Okay, so the primary thing here is to share nothing. No shared memory. Actors are completely isolated.
Yeah.
However, there is an additional tweak to it, and I mean, Erlang is a functional language which doesn't have any immutable state.
Yes.
So there is also this thing of requiring no locks on a much lower level.
Yeah.
So how does immutability and this functional modify nothing approach play into this?
The reason shared memory programming models are difficult is that two parallel processors can access the same area of memory and at the same time and make changes to that memory. Now that's a notion of mutable state. If you have immutable state, then variables in a language cannot be changed once they've been set. Erlang has what we call assign once variables. So having been given a value, they can never ever be changed. That means that the process itself cannot change them. But more importantly, it means that other processes can't change them. Since other processes can't change them, you don't need to lock these data structures. So everything can run in parallel.
Yeah. When I was reading the book, I actually wondered how important that feature really is. Because if you had mutable state within an actor and used message passing between them, then you would still achieve the actor level concurrency and no shared property, right?
Yes.
So I was wondering if I built an actor library on some other language that enforced those properties, then I didn't need a functional language that had the immutability concept on language level, right? Or is there a deeper?
You could do it that way. I mean, I think it's probably a historical accident that Erlang is that the individual processes are immutable, and that actually reflects the prologue history. Yeah. If it had started off as C or something like that with added message passing, we could have still done, say, a version of C.
MPI.
Yes, something like that, yes.
Which is the message passing interface, by the way.
But there are additional benefits to having non-mutable state. So in the book, I say when you debug a program, you have an additional benefit, because if you set a variable only once and you later observe that it's incorrect, there's only one place in the program where it can happen. But if it's getting updated all over the place, you don't know which of these occurrences was the one that led to the error. So it is actually very easy to debug.
Good point. You have these actors which serve as the active ingredients of a concurrency-oriented program. Now, if you build a virtual machine for Erlang or a compiler, however you do it, actually, is it compiled or interpreted, or?
Yes. Well, it's both.
Okay.
It's the first version was a pure bytecode interpreter, and that became a 32-bit threaded word interpreter, and then a group at Uppsala University built a hype compiler, which was a high-performance Erlang. That's a nice acronym.
Yes.
So we could hype it a lot. And so today what we distribute is, the machine changed became called Beam, which stood for Bogdan's Erlang Abstract Machine. In fact, we had 3 or 4 of these machines, all sort of named after ourselves in typical modesty. And so the current version is a 32-bit threaded machine, rather like Forth, with a native code compiler if you want it.
So in some sense, and that's what I was trying to get at, the virtual machine, of course, uses threads, probably thread pools or stuff to do things.
No, the virtual pool steals 2 threads from the operating system, and then it does everything itself. So processes are... I mean, Erlang is much more like... the runtime system is much more like an operating system than the normal runtime for... the normal runtime for a programming language is rather small.
Sure,
because everything's done with instructions through the compilation process. But in Erlang, the runtime system is enormous because it's doing an awful lot of what the operating system is doing. In fact, the operating system just basically manages files and sockets for us and gives us a large amount of memory when we start. And then we do it all ourselves.
We already mentioned MPI briefly in passing.
Yes.
So the question is, why is everybody doing shared memory, and are you the only guy who or the only community who does the message passing thing? So the question is there are other approaches or other languages, other tools that use the same kind of approach to concurrency?
There are, but I don't think they're as mature as Erlang. Erlang's kind of leading the pack when it comes to message passing concurrency. And I think the reasons for it have actually got nothing to do with speeding up things on multicores, because that's a modern phenomenon. The original reasons have to do with fault tolerance. So if we back to 1986, what we were trying to do then is to build a fault tolerant system. So I think software people don't really understand fault tolerance like hardware people do. So the first, I used to give a lecture. I still do give a lecture where I say, well, if you're going to make a fault-tolerant system, you need 2 computers. Everybody looks strangely at me and you say, well, come on, if one computer crashes, you're screwed. So you actually need 2 computers.
Or more.
Or more, yeah. You can have 3 or 4 or 5. Both of them might crash.
Sure.
And so if you're let's take a very simple world. It's only got 2 computers and we want to make a fault-tolerant system. It's pretty obvious that you have to copy all the data from one computer to the other that you need to do a recovery. If computer number 1 crashes, you take over on computer number 2. And that means that you can't have any dangling pointers. You must have copied everything you need from computer 1 to computer 2 in case computer 1 crashes.
Sure.
So that's the reason for copying everything. It's got nothing to do with concurrency. It's got a lot to do with fault tolerance.
Yeah.
And so that's the kind of raison d'etre for Erlang. That has an inevitable cost because People want to say things like, well, I would like fault tolerant to cost nothing in the case where the system doesn't crash. But that's just not possible because if you make a fault tolerant system, you need 2 computers, you need to copy all the data over. If they don't crash, you could have just had a dangling pointer. You could have copied less data, but it won't work in the presence of errors. The additional benefit which we saw years later was once we've copied everything, we now need to lock everything, and these 2 machines can work in parallel on that data. But I don't think that thought wasn't in our heads, back in the mid-80s.
Yeah. It's interesting to see. We had a couple of episodes on distributed systems, and in the distributed systems world, it's well known that message passing is a good way to do it. Obviously, you can't have shared memory over physical, your Sweden, Australia example.
Yeah.
So in addition to Sequential Erlang, which is a functional programming language with pattern matching, we'll talk about that later, and Concurrent Erlang, which allows you to basically spawn every function execution into a separate actor, there is also distributed Erlang. So how is that different?
The model's not different.
That's the point.
That's why we have concurrency-oriented programming. In this model, we just have message passing, and it uses what we call location transparency. This is just the idea of if you know the name of somebody, you can send them a message. It's like email or popping a letter into the post. Yeah. How you actually implement that is a kind of, well, it's not a detail, but
you mean how the VM does it?
Yeah. So here are two alternatives, or four alternatives. One way of doing it is to have two virtual Erlang machines running on the same physical processor. Mm-hmm. These are separate address spaces with their processors and everything. Then the programmer themselves manages the namespace. They say, well, I want to start a process in node number 2 or node number 1, and you can have as many nodes as you want. That's very convenient because you could put, say, 10 nodes on one processor, one sequential processor, and you can test a distributed application. Then you can deploy it in a real distributed application by moving these nodes to physically separated computers, possibly in different countries. That's one model of distribution. The other is that you map these nodes automatically onto the cores of a multi-core computer. And then you don't need to know about the nodes. And there's a completely different version of the Erlang scheduler, which will just schedule randomly onto one of these. No, it's not random. It's a round-robin scheduler. Yeah. But the details don't really matter. Yeah. And in the implementation, we will improve those algorithms and things. So in that version of Erlang, the Erlang programmer sees a world where there's only one node, and the virtual machine maps processes onto the physical cores in the CPU. Mm-hmm. Mm-hmm. But all of this makes virtually no changes to their program.
That's the nice thing, actually. I mean, if you want to evaluate a function in another actor, you just basically say spawn, and then you specify the function. And if you want it on another node, you say spawn function, then add name of the target node. That's pretty neat.
Yes. And just all the data in the closure just whizzes over to the appropriate node without you having to do anything.
Yeah. Nice. Okay, so let's leave the concurrency aspect behind for a moment, and let's look at the fault tolerance aspect. By the time we broadcast this, we will have had the double episode with Bob Henry on fault tolerant systems, so you listeners should know what it's all about to build a fault tolerant system and some of the patterns. And so in Erlang, there is this thing called let it crash, let it die.
Yes.
So what's your model towards fault tolerance there?
The model of fault tolerance the fundamental model is that of handling errors remotely, not locally. The reason for that is if we go back to our two-computer situation, we have two computers, one of them crashes. The error must be handled on the second computer. If the first computer crashes, we can't handle it on the first error. There is no computer to handle it on. Yeah. So this introduces very early on the notion of remote error handling. So if process 1 crashes, process 2 will fix it up. So basically we try not to fix up the error in process 1. Okay, there is a try catch exception thing inside one process. Just because if it's a trivial error and you can deal with it, then you do so. Yep. The model we build is basically what's provided in the language is a reporting mechanism. So if one process dies, another process gets an error message and says, hey, this process died.
You can link processes, one being the supervisor of the other one.
That's right. So it's rather like a human organization.
Sure.
Because it's very easy to understand. We have workers and we have supervisors.
Yeah.
The workers do the jobs and the supervisor just watches the workers. If a worker dies, the supervisor gets informed and he starts a new worker. So the workers are not supposed to fix errors. They're not, we even have programming rules. We tell them they're not allowed to fix errors. This makes a very, very clean programming model. So it's very strange. In all languages apart from Erlang, you're encouraged to do defensive programming. In Erlang, we're not encouraged to do defensive programming. Yeah. We have what people call happy case programming. We only program the happy case, what the specification says the task is supposed to do. You see, I think one of the troubles which I met early in programming was when writing code from a specification, the specification says what the code is supposed to do. It does not tell you what you're supposed to do if the real world situation deviates from the specification. This is an enormous class of things. It doesn't tell you what to do if it doesn't follow the spec.
Yeah.
So what do the programmers do? They take ad hoc decisions. This is crazy. This is lunacy. And this leads to about 30, 40, 50% of all code is this error checking code to allow for the cases which are not in the specification. Now, the specification doesn't tell you what to do. So the Erlang approach is let it crash. If you deviate from the specification, you crash.
Yep.
And the supervisor process detects this. So the worker's going along and it says, it's like a really top-down, strict, brain-dead organization where the worker encounters a situation they don't know what to do. Yeah, right. And so they die, and their supervisor gets a message, hey, I've died because this thing happened that's out of spec. So what does a supervisor do? He says, make sure all the invariants are obeyed. Now, the invariants are things like closing files, closing sockets, cleaning up behind you. Yeah. So it doesn't matter how an error occurred. It's irrelevant because we put it right with the invariants afterwards. Now, this error goes into the error log. And when we look at the error log, we can say, okay, what happened was this worker gave up because this funny thing happened. Yeah. And then the system was put back to rights again. And then we can make a design decision. Do we wish to code for this case? Or is it so rare that it's never going to happen again?
Oh, yeah. And that brings us nicely to the next point. So if this thing really has to use the correct terminology, I think a fault somewhere in the code, you might want to replace this module, actor, whatever. So that's where, if you want to run the system forever, you need this dynamic on-the-fly updateability. That's something else that Erlang brings?
Yes. And in fact, here's the funny thing. When you have deep concurrency in your language, lots of processes, things like code upgrade actually become easier than in a sequential language because, let's imagine we've got 1 million processes and, 1,000 of them are executing code that's got some little bug in. But the other 900,000, I don't know how many I said, those ones, we don't want to bother those guys, okay? Yeah. So they can just carry on doing what they're doing. If we can track down the 1,000 processes that got the bad code in them, we can change the code in those ones and leave all the rest alone. Okay. Now, if you only have one process,
that's a problem.
You're screwed.
Yeah. So one impressive number, I don't know where I read it, was probably in the book, was that using this approach you achieved 9 nines for some kind of switch system.
This was an Ericsson asynchronous transfer mode switch called the AXD301. That figure of 9 nines is kind of bloated around in a lot of blogs and things, and doesn't represent an average behavior. It represents a best case behavior that was observed once, and British Telecom observed this and reported it. And when we asked them, I think for detailed figures, or was this a systematic study? No. So it's more apocryphal than hard science.
But it's still pretty impressive. The order of magnitude.
It is the sort of top of the mountain. I'm not saying that all systems run like that, but aiming at 7 nines or something like that, it's that's realistic.
So if you want, since we talk about actual, real, achievable performance, let's briefly go back to the concurrent thing. What is the scalability? Do you really get linear scalability? How much does this depend on what you program, on your structure of the program? What's some of the best practices to make a program scalable?
Yes, right. This is very early days because to start with, there aren't many multi-core processors with large numbers of processors around. The largest one you can get your hands on is probably the Sun Niagara, which has got, 8. It's got 8. I think they're up at 64 cores now, but I've played with the 8-core version with 4 hyperthreads per core, which some say is equivalent to 32 hardware threads. Now, what we see there is programs that have a large amount of computation and a small amount of data in the messages scale linearly up to about, say, 20 processors. Above 20 processors, sorry, not processors, 20 cores. When we go up from 20 to 32 cores, the curve flattens off a bit. And I don't think we understand why. And, somebody might understand why. We have to investigate the cache behavior and things like that. But that's very encouraging. Then the entry level to concurrent programming, the dual cores. I mean, you can't really investigate. You don't get many plots on a graph when you've got 2 points.
Yes.
So you can't see if it's linear.
Sure.
You just get 2 points. But it's very encouraging. I mean, Ericsson's shipped a product on an dual core AMD, which was virtually twice as fast as the one that was running on a single core, and everybody was absolutely delighted. I mean, so here the programmers are, because our programs are all written in Erlang, we're sort of ready for concurrency.
Yeah.
So when they ramp up the number of cores, we tweak the program a bit, bung it in, and measure how fast it goes.
Yep.
So we see this as a great commercial advantage.
Sure. And to make it concurrency ready, it basically means that you should have as many actors as possible, because if you have few processors, cores, it's, just scheduled on several ones, and if you have many, it's just going to fill up.
Well, it's not only that. You have to get rid of the sequential parts. There's something called Amdahl's law, which very easy to understand. I mean, Amdahl's law says, well, for example, if 10% of your application is sequential, then you'll never be able to go faster than 10 times. And the reason for that is, if you think about it, 10% is sequential, 90% is concurrent. But this 90% can be just made to shrink down to 0 with enough processors. So you're left with the 10% which you can't do anything about.
Sure.
So really chasing the sequential code out of your application is the thing you'll have to do to make it go really, really fast.
And of course, you can only do that if the overhead of making something concurrent is very low.
Yes.
And that's the whole point.
That's the point, yes.
Yeah.
I think you're absolutely right there. That's a key observation, because on the chips, there are 2 types of concurrency. There's instruction level parallelism, which is deep pipelines, and then you've got thread level parallelism, and that maps onto multi-cores. So there isn't actually another parallel mechanism.
Yeah.
Parallelity, that sounds awful. But there's not another mechanism for parallelism there. So really, now, since you're doing thread level parallelism, the programmer has got to make the decision, is it worthwhile the effort of spawning a process on a new physical processor? Because if it's a very small computation, it's not worth the effort of sending it off to another processor. Yeah. And I think only the programmer can make that judgment. Yeah. And I'm pretty sure that's right, because right since the 1960s, there have been research programs to automatically parallelize programs, chiefly Fortran for supercomputing applications. Yeah. And these projects have never succeeded. Well, they've succeeded in a minor sense. They've managed to speed up things by 15%. And that's saying, okay, we'll let the compiler or the analyze this program and figure out what we can do in parallel. Yeah. I think the programmer is much, much better at doing that. They know, or they should know, a good programmer has a performance model in their head, and they say, well, I know this is a big computation, and I know it's isolated from that, so I'll spawn it off in a separate process. It's just that the nuts and bolts of doing that in C or Java is extremely difficult. It's painful, but it's very easy in Erlang.
Yeah. So when I read the Erlang book, and even more when I was in your talk Monday, I got the impression Erlang isn't really a language. It's a system, an operating system, with a language, of course, but there is a lot of infrastructure that makes all these things possible. It's almost like a little bit of an application server. I mean, if you compare that to some of the enterprise application servers, you will see many commonalities.
Yeah.
But in order to build real systems, you actually do deliver in the package additional infrastructure with database applications.
Yes,
can you a little bit talk about the OTP framework?
I think we have unfortunate naming here, because actually, I don't think I've ever said Erlang wasn't a language. Erlang is a language.
Well, sure, I said that was my impression.
Yeah. So what's OTP and what's the runtime system? I think to give you an analogy, I think if you say, well, okay, Erlang's like C. The runtime system's like Unix, and OTP's like Ruby on Rails. It's an application framework. It's just got a very unsexy name. I mean, sure. if we'd just called OTP on Rails, everybody would be using it. So OTP is an application framework, and it's got all the kind of goodies you need to build fault-tolerant system. So we're familiar with application frameworks, things like Ruby on Rails that help you make web applications, but we're not familiar with application frameworks that help you make unsexy things like fault-tolerant software that runs forever. Yeah. So that's what OTP is. It's Erlang on Rails or whatever you like, but for building fault-tolerant applications. And the runtime, that's the operating system.
So the ingredients is a database, I guess,
yes.
and some kind of probably server component.
Right. So the main ingredients, yes, as you said, there's a there's a database. Now that's a very interesting database. It's tailored for real-time use. It reflects its heritage. It was done for telecoms applications for Ericsson. We use it in telecoms applications. So it's RAM resident. Well, that's not strictly true. You can define tables in it. It's a DBMS. It's rather unique, I think, in that once you've defined the tables, you can specify where physically the tables are and how they are. For example, you can say, I want a RAM replicated table on 2 machines, and that's for fault tolerance. Or you might RAM replicate on 2 machines and disk replicate on 1 machine. So you spread the tables over 3 machines or 2 machines, or you might have a fragmented table that you spread over 50 machines if you have a colossally large data set. It's very flexible. And of course, it understands about Erlang data terms. So it's what we call an object database. Yes, you can put any tuple.
Yeah.
You don't have to serialize something. If you want to store an XML parse tree in the database, it's a single instruction, and bang, in goes your XML parse tree.
Yeah.
There's no messing around. It's an object store.
Yeah. Okay, so then let's look at the other extreme. We've looked at all the infrastructure, distributed, concurrency, blah, blah, blah. Let's look at sequential Erlang. Erlang is a functional language. Can you give us a little bit, some pointers to what some of the interesting features are?
It's a dynamically typed functional programming language. So functional programming language is split into a number of different schools. All functional programming languages are based on the idea of immutable state. Immutable state's another way of saying they have no side effects.
Yeah.
And what you learned in school was that side effects, especially when they're hidden, are evil.
Yeah.
So that's why, that's what you do in Java all the time. You put them in a method, you hide them away so that your programs crash. And our functional programmers don't believe in that. They believe in something called the lambda calculus. Now, the lambda calculus is a pure calculus for how you perform computations. That has spawned off several kind of families of functional programming languages. You have the polymorphic, strongly typed languages, like Haskell and things like that, and then you've got the language without a type system. They're still safe. The languages like Scheme and Erlang. So Erlang's in this dynamically typed part of the functional programming language, but it still has all these notions of higher order functions, immutable state, and things like that. So it's a proper member. It's a proper member of the functional programming language community. So we see different functional languages, which I think are appropriate for different tasks.
Mm-hmm. Can you give us a very short intro to what pattern matching is? Because that's a concept that Java folks and probably mainstream people don't know.
Yep. Pattern matching is, we don't use if statements and case statements, and we do actually, but to a much lesser extent than normal programming language. We just write patterns that are matched. That doesn't sound.
And that's in the function declaration.
That's in the function declaration.
So you have different variants of the same function with different patterns that match the kind of
it's a way of doing polymorphism.
Right. So structural polymorphism in some sense.
Now, what the pattern matching compilers do, they take these patterns and they actually compile them into trees of if statements and switch statements and things. Yeah. But they do it probably in a way that is more efficient than you or I could do, because they optimize these things. The main consequence of pattern matching is that the programs are extremely short. Because the programmer doesn't have to think about, do I write a switch statement or a case statement or an if statement? They don't write these things. They just write the patterns, and the compiler produces these things for them.
Okay, so I think that was all the technical stuff.
Yeah.
Let's look a little bit about, to wrap up slowly, at how the language was designed. I kind of thought that, you did.
I think designs are kind of.
Well, okay. how it happened that
how
there
it
was.
grew.
Yeah.
Yes.
So, I mean, you were kind of visionary in some sense what concurrency.
Yeah, I don't think we thought we were visionary at the time.
No, okay. So what I'm about trying to get at is that maybe if it wasn't designed, we shouldn't either call it a process. So what were the sequence of accidents that led to Erlang?
Well, as I said, we started off, I joined this really newly started computer science lab at Ericsson back in about 1986. Yeah. And we'd just got, I think we were the first people in the company to get a Unix system, because people said, you can't use Unix, it's a sort of virus, it must not be connected to the rest of the corporate networks. Nobody believed in Unix in those days. And we had a VAX 11750. So basically, we interpreted computer science as just programming telephony in every programming language that there was a free implementation for the VAX 11750. That was our definition of computer science. And we just sort of tinkered around. So this wasn't a process. What we actually did, we programmed the same problem, which was just POTS. We had a little we had a little hardware telephone exchange, a PABX, which we controlled from these different languages. And we wrote telephony in Ada and Concurrent Euclid and Prolog and Smalltalk and ML and all these languages. Mm-hmm. And we actually published some research on this, and we just saw how easy it was to program. So what happened then was I was sort of grafted into this project, and everybody was doing their own little ways of programming it. So I used Prolog and added processes to it. And this very slowly sort of, one day it had gotten a name. We actually said, well, this is sort of a little programming language. And then we thought, let's try it out on some users. And we managed to find some users, and they said, this is great. I mean, they liked it. Mm-hmm. They were really enthusiastic. And things kind of dithered along, and they liked it. It wasn't fast enough. They wanted features. We added the features.
Sure, so you grew the language,
yes.
Really.
And in that day, I mean, that was just me and them. And, a complete rewrite of the system took, a day or 20 minutes or something like that. It wasn't long. And, my boss Bjarne used to say, what's Erlang? He says, well, it's whatever Joe defines it to be today. There was never a big specific, I don't think. All this kind of, when I give a lecture and we say, here are the requirements for the language, that's an after-the-fact construction. That's what we wrote down afterwards to explain what we'd done.
Sure, yeah.
We never had a set of requirements.
Well, implicitly you had.
We had them implicitly. I think the culture, we worked for a big telecoms company. The culture sort of, the requirements were sort of seeping out of the walls. So they were in the culture.
Yep.
And so we built this. We tried it out on some users. After about a year, I worked on it alone, and then Robert Veerding joined me. And Robert, as usual, said, can I make a few changes to your program? And I said, yeah, sure. And then typical Robert, he rewrote everything, and I think what was left of my program after you made a few changes was one comment at the top that said, Joe started this, and changed every single line of code. And then there were two of us. And then about a year later, Mike Williams came along. And then there were three of us. And at that stage, they wanted it to go faster. Mm-hmm. They'd decided that they could deploy Erlang if it was 80 times faster.
80
to 0, because this was a Prolog interpreter at the time. It was very slow. So we kind of scratched our heads and thought, how do we make it go faster? And we decided to then do a bytecode interpreter.
And that's written in C, I guess, today, or?
Well, yeah. So we, at that stage, I started writing a bytecode interpreter, and I wrote it in Prolog. Mm-hmm. And of course, it didn't go faster, it went slower. So going from about, the Prolog version went about 1,000 inferences per second. It went down to 4 inferences a second. And I said, yes, but there's a cunning plan. We'll replace the slow interpreter with a C program. And then I started writing C. Now, I'd never written C before. I used to write Fortran until Mike saw my C and wanted to puke. And said, Joe, that's the worst C I've ever seen in my life.
It looked like Prolog, I guess.
Yeah.
Tried to look it like Prolog.
Yeah. And so Mike came along and he wrote an emulation in C. Mike was pretty good at C. And he really, I think he and I sort of, he taught me quite a lot about C. And Mike had a lot of experience with concurrent languages. And so he said, well, the performance of a concurrent language is predicated by 3 things. It's a context switching time, it's a message passing time, and it's the time to create a process. So these are fundamental. In any programming language, you start with something that's fundamental. And you implement that very, 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 very well. Yeah. And then you build your tower on top of it. And so what Mike did in the emulator there was he wrote the C, and then he turned on the optimizer and he printed out the assembly and sort of stared at it, and then he rearranged the C and did it again and again and again.
Yeah, but for these kinds of low-level virtual machines, it makes sense to tweak the details because it scales kind of.
Right. And so we tweaked the details out, and then we made the first bytecode interpreter, and that was that was before the JVM and things like that. We deployed it, and I can't remember what it was. It was more than 80 times faster.
Mm-hmm.
It was 100 times faster, something like that. And the product team said they had revised their estimates and wanted it 280 times faster. As usual. And that started this long road of sort of rewriting and making it faster and so on. And that carried on until it was turned into a register machine, and Bogdan Hausman took over the
that's
the
Bogdan and Beam.
Yes, that's right. Yeah. And he re-engineered the machine for a register machine, and we got researchers in. So it and Klaus Wikström joined after 4 years and added things like the real-time database, and he added distribution. We'd always planned distribution, but we'd never actually implemented it. I mean, it seemed just, we've just got messages and things, so it must be easy to implement. Because it was easy to implement, we never actually did it. And it sort of grew from this very rapid prototyping cycle where everything took a day to rewrite the complete system. And now it must be up in I hate to think, 6 months or something.
Sure, to make it. It's highly optimized.
Yeah.
Okay, to wrap this thing up, why don't you give us a little description of what the community is today, how the book is going, just to give what's behind the hype these days?
I don't know. It's gone berserk. It's crazy.
Yeah, that's true. Yeah.
I mean, if you look at Reddit and things like that, you would think there are only 2 languages around. There's Haskell and Erlang, and they're fighting out for mindshare.
Sure, but that's not.
But I mean, that's among people who kind of get turned on by programming languages. Yeah. People seem to be flocking to the language. I mean, if you just search for Erlang blogs, there's 4 new ones. Go into Google and do blog search on Erlang. You'll find sort of 4 new ones a day. Now, I'm not saying they're all good. Some of them are extremely good. Some of them are kind of not so extremely good. But that's not the point. The point is this interest that's there. And then we've got 1 or 2 flagship applications. Telephony applications and databases aren't sexy stuff.
Sure.
They're kind of boring.
Yeah. I
think the flagship application is eJabbered, which is a Jabber server, and that was written completely. I think the exciting thing is can Erlang spread sort of outside its community? Can we see spontaneous growth from people who've just picked it up off the net? And we're seeing lots of that. We're seeing a lot of companies being formed that use it. Interestingly, I think we're seeing a lot of companies that use it and make money. We're seeing a lot of companies that put Java competitors out of business. So this is, and people know about that. The word is spreading.
Yeah,
the venture capitalists know about it, so they're financing the companies. Yeah. And that's very exciting.
I saw this blog post by Ralph Johnson who suggested that Erlang might be the next Java. So it seems to be taking off, really.
Yeah, I don't know if that's true.
I also found maybe a bit optimistic.
I was thinking about this, and I think Erlang might be kind of in the way that languages are, it might be like Smalltalk. Because if what happened with Smalltalk was the language that did object orientation right. They got it right. And the good ideas were taken from Smalltalk and grafted onto C and create and cause the creation of languages like Java. Now, Smalltalk always had this passionate community that said, well, we do object-oriented programming right. Yeah. And all these other people have just stolen a few of the ideas. And, well, not stolen, but they've included these ideas in their languages. So what might happen with Erlang is that it has this passionate community that says, well, we do concurrency-oriented programming right, and that other people graft these ideas into their languages. So we might see Java++, that has the Erlang concurrency model.
You might have heard about the Scala people who put the actors framework into it and got really good concurrency.
Yes.
So that's,
Yeah, I mean, that's But I think they would really have to, I don't know how they've done it.
They also have closures and some of the pattern matching. So,
right. But I think there would be a case for re-engineering this from, as I said earlier, in the Erlang virtual machine, you have to start with the process spawning mechanisms, with the context switching times, with the message passing times, really low level in the virtual machine. Yeah. And then you build that up. If you don't have instructions in the virtual machine to do that, you have to emulate it.
Yeah.
That's very inefficient. So if you want to re-engineer a virtual machine, like the JVM or something like that, adding instructions to create processes and things, and then build something on top of that, I don't think you could graft in the existing infrastructures. I mean, the trouble with Java is if you say, well, let's make Java++, so that we can use all the libraries, but the libraries are using this shared mutable state stuff, so it's not really going to work. But re-engineering it could work.
Yeah. Well, as long as it has curly braces, I think that's going to be the next big language. Anyway, okay. Did I forget to ask anything you want to say?
The bit syntax.
Oh, the bit syntax.
Do you want to ask me about the bit syntax?
No, this is really cool because it's a DSL, which is my kind of pet peeve, a DSL for parsing bits in a byte stream. So yeah, give us the heads up.
Yeah, the bit syntax is something that was added to Erlang by Klaus Wikström as an afterthought, and Tony Rogal, I think, did it as well. And what they observed was a lot of time they're just unpacking data structure. I mean, they're unpacking bits out of words. So, have you ever tried to extract 7 bits out of the middle of a 32-bit word? You do sort of X bit shift left by 8 bits and 0xFF. Now, what the heck is that in? Do you know how you do that?
No, I can't do that.
Yeah, it's horrible, and of course you get it wrong.
And actually, my approach would really be, since I'm into this DSL stuff, to write a DSL that specifies exactly what I want.
So that's exactly what we did, and we extended pattern matching over bit fields.
Yeah.
So now you can say, this is 7 bits, this is 3 bits, this is 2 bits, this is 9 bits, and that gets compiled into pretty efficient code. So in the book, my favorite example from the book is of course, it's an MPEG-3 streaming media server, which implements the Shoutcast protocol. And what you have to do there to get it right is to synchronize the server with the actual MPEG-3 frames. Mm-hmm. Now, this is just about as low level as you can get. But it's written in Erlang, which is a high level language. So you just define the bit pattern which defines the sync frame in MPEG-3. And then you just trundle down the data looking for this. And once you've found it, you just stay in sync. The code is really easy to understand. And it's a nice example of something where if you put the specification on one side and you put the code next to it, it's isomorphic. Yeah. So it's very easy to understand.
When I was in your talk, I think Magnus Christensen from Intentional was also there. We looked at each other and said, hey, this is a really good example for a DSL. So it's really,
and I think this is one of the sort of things where you see in a lot of that can be grafted onto a lot of programming languages.
Yeah, absolutely, no problem.
And I've always wondered why do regular expressions go over bytes? Yeah. Why do they go over bits?
Yes.
It's very easy to make a regular expression matcher that matches over bits. And it's very useful.
Yeah, absolutely, especially if you're in this kind of low-level area.
Yeah.
Okay, Joe, thank you very much for being on the show. I appreciate it. It was very interesting.
Thank you.
Bye.
Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.